So welcome everyone to this new cycle of young seminars, which are seminars, as you know, organized by the Italian Society for Statistical Physics. Usually we have a couple of speakers, but this time we have only one, just basically for technical reason. And the speaker is Chiara Calascibetta, which I'm now going to introduce briefly. She is a PhD student at the University of Tor Vergata, Rome, under the supervision of Luca Biferale and Massimo Cencini. She's going to finish, I think, in December, right? Yes. Okay, so this is the present. Regarding the past of Chiara, let me just mention that during her master studies, she received quite a number of prizes, like, for instance, the Enrico Persico Scholarship, which is a prize which is given by the Accademia Nazionale dei Lincei to the best master student in physics among all the universities in Rome. And also this, her thesis was awarded the Woman in Theoretical Physics Prize, which is a prize given by ENFN. Actually, her research activity focuses on the study of active particles advected by turbulent flows. And this is also the subject of the talk today, whose title is Optimal Strategies to Catch a Passive Drifting Target in Turbulence. So, Chiara, you can start. You have half an hour. Thank you.
Okay, so you see my screen?
Yes.
Okay, let me just reduce this. Okay. So thank you very much for the introduction. And first of all, let me thank all the organizers for having invited me to present my work here. So it is a pleasure for me. So today I'm going to speak about optimal strategies to catch a passive drifting target in turbulence. And in particular, this is one of the main work that I've done during my PhD within the group of Luca Biferale. And this work is done in collaboration with Francesco Borra, Antonio Celani, and Massimo Cencini. So before going into the details of the problem of catching a target in turbulence, let me just contextualize this work within the literature. So we are working in the context of optimal navigation problems. So with optimal navigation, we refer to all the cases in which we have an active particle or a microswimmer that has to optimize its dynamics in order to achieve a specific task, a specific goal. And a typical problem of optimal navigation is the so-called path planning problem that consists of going from a specific region of the flow to another region in the minimum time. So, of course, if you imagine to do not know anything about the underlying velocity field, the only thing that you can do is to follow the so-called trivial policy. So the trivial policy that is shown in green that consists of particles that simply continuously steer towards the target direction. So, of course, these strategies are not optimized at all and are very suboptimal with respect to strategies that instead are optimized to exploit the underlying velocity field. Like, for instance, the blue curves, so the trajectories that follow the so-called reinforcement learning strategy, that instead is a strategy optimized by data-driven techniques. Okay, these kind of problems have been studied in different ways, in different setups, as I summarized here. So, for instance, we can have cases in which, in this paper, the authors investigate the case of very simple flow, so the simply a zigzag flow. But here, the model for the microswimmer is very interesting. Indeed, here they consider a microswimmer that is pulling a cargo. In this other work, instead, the microswimmers are modeled as undulatory microswimmers, so in order to mimic the behavior of natural bacteria. And then in this other work, instead, the model for microswimmer is very simple, simply a point particle, but the environment is very complicated. Indeed, here the author considered optimal navigation problems in curved manifolds. In this other work, instead, the environment, the underlying velocity field is very complex. Indeed, the authors consider 3D turbulent flows. So all these problems, as you can see, are very different, but in any case, all the works that I just mentioned, they all involved the optimization of a single particle trajectory. So in optimal navigation, however, we can also have problems related to the multi-agent task. multi-agent dynamics. So for instance, in this other work, the author considered a problem in which two competing micro swimmers are engaged in a push evasion task. So in this case, there is no velocity field, but the two micro swimmers can sense hydrodynamic disturbances induced by the other particles. So as you can see, we have a variety of problems on optimal navigation. And so in particular, as you can see, optimal navigation is a very growing field in the context of active matter. So in particular, all these problems can be studied and tackled within the framework of control theory. So in control theory, as you can see, we have different approaches, different methods, and in particular, they rely on two axes of knowledge. So these axes, the x-axis, quantify the knowledge that we can have, that we can exploit by the dynamical evolution of the system. So we can go from model-based approach up to model-free approaches. Then instead, in the y-axis, we have the degree of measurements or observation that one agent can perform inside the environment. So in our case, imagine the degree of measurement that the active particle can perform inside the turbulent flow. So if we imagine to know everything, so we have both a full observability and also a perfect model for the dynamics, we can solve the problem analytically using optimal control theory. So in this case, we know that we cannot do better. Or if the dynamics is defined in a coarse-grained manner, we can solve the problem using Markov decision processes. However, of course, in realistic scenario, this is a very idealized case because in realistic scenarios, you never have a perfect observations. And so you should consider instead to work with model-free approaches. And one typical example is the reinforcement learning method. So reinforcement learning instead is optimized by data, by trial and errors. Okay, both reinforcement learning and optimal control, in any case, are optimization methods that work for long-time optimizations, so long-term goals. In the middle, instead, I introduce these heuristic strategies where they are in the middle because they are neither model-free nor model-based, but they are based only on an approximation of the real model, of the real system dynamics. And in particular, as we will see during this presentation, I call them reactive because the idea is that now I want that the active particle simply can measure some instantaneous information about the flow, and then it can immediately know how to react in the environment. Okay, now I will focus on the top right corner of this diagram. So we are dealing with optimal control problems, and in particular, as I said, typically in optimal navigation, you have to optimize the dynamics of a Lagrangian particle or a particle in the fluid. So dot x is the dynamics of the particles, v is the typical velocity field, and u is the control variable. Now, the control variable is typically considered very small compared to the underlying flow, and this is indeed why we indeed need an optimization criterion for the dynamics. And now, why? Because we are working with optimal control, because we want to approach the problem with optimal control problems, with optimal control methods, we require full observability for the system. In particular, we require full spatio-temporal observability. In other words, this means that we should know exactly how the flow would evolve at all times and at all space in the future. And we also should know where the particle can go in the future. So we know everything. Now, given these assumptions, we work in a similar problem, but we, instead of considering the simplest path planning problem of going towards a fixed target in the space, for us, the target B is a moving target. So we considered this problem and we published this work last year on communications physics with the title Optimal Tracking Strategies in a Turbulent Flow, and this is the main focus of this talk. So here there is the setup for the problem in which we have two particles and the goal is to minimize the separation between the two. But I don't want to enter in the details of the setup now because I will do that in the following of this presentation. Instead, what I would like to do is to focus on why it is interesting to control and to study the dynamics of relative particles in turbulence. So navigating in a turbulent environment is not at all an easy task. This is because we know that turbulence is a multi-scale problem. Indeed, if we look at the energy spectrum in Fourier space, we immediately realize that we have, as sketched here, that we have an energy distribution that covers many range of scales. In particular, here we have the so-called inertial range that is very large. In particular, all these different scales are coupled by nonlinear dynamics, and this has a very important consequences in turbulence. That is the so-called intermittent statistics of turbulence. So this means that if we look at the distribution, at the statistics of the velocity field at different scales, we realize that we have different statistics for different scales. So in particular, this is more quantified here, where I show the PDF of the statistics for velocity increments at different scales R. And so we can see that for large scales, we have Gaussian distributions, while for smaller and smaller scales, we have distributions with very fat tails. So this means that when we navigate inside a turbulent flow, there is a non-zero probability to encounter an event that is up to 40 times the standard deviation. Of course, this has very important consequences when we look at the dynamical evolution of Lagrangian particles in such flows, and in particular, also the dynamical evolution of the separation vector between two-point particles is strongly dependent on these dynamics. This is the focus indeed of this presentation. So, if you look at the separation vector between two-point particles in such flows, when the particles are very close by, so in the so-called small-scale separation regime, we know that the particles experience Lagrangian chaos. And so we have that the separation grows exponentially in time with lambda, that is the Lyapunov exponent. When we enter in the intermediate range of scales, so where we are beyond the so-called Kolmogorov scales, when we have Richardson dispersion, so the square of the distance grows like the time to the cube, and then at very large scales, we enter in the diffusive regime. Now, this talk focuses on the first regime. So at the end, our aim will be to study and control this exponential expansion for the separation of the particles. So, which are the objectives of this talk? We want to invent in silico experiments to control and study separation of Lagrangian pairs in turbulence. Then we want to learn how to avoid or exploit such intense fluctuations when navigating inside a flow. And then we want to understand which are the potentiality of control tools for Lagrangian turbulent problems. So control tools that we know that can be equation-based, so analytical tools like optimal control theory or heuristic strategies, or data-driven approaches like reinforcement learning. So this is the setup for our work. So we are working in a 3D time-dependent turbulent flow. We have one particle that is simply a tracer inside the turbulent flow, so it's shown in yellow, is the drifting target, the passive target. Then in red, we have the active particle that instead can control its dynamics. How we model the control in the simplest possible way. So we fix the velocity amplitude, the swimming velocity, to be small enough compared to the velocity of the underlying flow. And then instead, we have a navigation direction that is the quantity that indeed need to optimize in time. Now here I just put this figure just for a possible application. So imagine that we have some drifters that are released in the ocean in order to optimize the data acquisition capabilities of a specific region of the flow. So of course, this is a typical example in which you need to control their trajectories in order to improve the quality of the observations. But okay, this is just an application. So instead, let me focus on our problem again. So I said that we are interested in controlling the small scale separations. So this means that we always initialize the particles to be below the so-called Kolmogorov scale. So in other words, if we are below these scales, it means that the velocity field is smooth, and so that the two particles experience the same local gradients at their position. If we do that, we can rewrite the velocity at the active particle positions in terms of the velocity at the target position plus these gradients. And so at the end, we can rewrite our system in an adjoint way, study directly the separation vector R, so this linear dynamics. So now we have that the control variable must optimize a linear dynamics. Anyway, the problem is still non-trivial, because in any case, the gradients that appear here exhibit all the complex statistics that characterize turbulence. So we know that we have a non-Gaussian PDF, strong fluctuations in time, and long time correlations. Now, I want to show you how it is possible to apply tools from control theory to solve this problem, and I will start focusing on optimal control theory. So from optimal control theory, we have different methods that in principle we can apply, but the most suitable in this case is the Pontryagin minimum principle. So this method is, at the end, is based on calculus of variation method, and the solution is obtained as the solution of a constrained minimization problem. Now, I just want to give you the key ideas, and so let's follow the key steps. So first of all, we have to define a cost function or a performance index that we have to minimize. So the cost function is composed by two terms: what happens at the final state, at the final time, and what happens along the entire trajectory. Indeed, here TF is the time horizon for the optimization problem. So at the final time, we want to minimize the distance because we want to be as close as possible. While in time, we want to minimize, we want to minimize the time of arrival at a specific distance, a captured distance, a desired distance. So here theta is the step function, the Heaviside function, and RC is exactly the captured distance that we fix to be small enough compared to the initial separation. Now, while we are minimizing this cost function, anyway, we have to take into account that we have some constraint that must be imposed in the dynamics. And in particular, we have to impose the correct dynamical evolution of our system, so this linear evolution. And then we have also to consider that we need a normalized navigation direction. So how can we enforce these constraints in the minimization problem? Through the formulation of Lagrangian multipliers. Okay, I don't enter into the details, but at the end, once you enforce these Lagrangian multipliers, at the end, we are working with a constraint minimization problem. And if you minimize the full cost function with the Lagrangian multipliers, you reach an equivalent of the so-called Euler-Lagrange equations. So you immediately realize here that we have a backward evolution for the phi variable, where phi is indeed the Lagrangian multipliers that are enforcing the correct dynamics. And then you realize that there is a direct connection for of the control variable with this dynamical evolution of phi. So at the end, we are dealing with a two-boundary value problem. So it's not difficult to imagine that finding the optimal solution is computationally very heavy, because at the end, we need to perform an iterative forward-backward search until we converge to the optimal solution. Okay, let me just stress one point more on this side, that is that even though we are dealing with a linear dynamics, finding a control that in time is able to minimize the cost function is still non-trivial, because there is always the velocity amplitude here, the swimming velocity, that defines the control, and we fixed the swimming velocity to be small enough that does not guarantee that the system is always controllable. So in other terms, this means that sometimes the agent, it will never be able to capture the target. It will never be able to become closer enough to the target particle. And if it happens, then the integral becomes simply a constant and the performance index becomes simply equal to the time horizon. But anyway, the optimization problem is still well defined, because in any case, thanks to the first term, and because in any case, we want to become as close as possible at the final time. So this is for what concerns optimal control solutions, so the case in which we assume a full knowledge of the dynamical evolution of the system. Anyway, we know that in realistic situations, we don't have such full knowledge, perfect observability on the environment, and so we should opt also for more realistic strategies. So here I work with the reactive strategies, where reactive means, as I said before, that we want to measure some information about the environment and we want to immediately know how to react in the system. So the simplest thing that you can do is to follow the pure pursuit strategy. So you simply navigate toward the target direction. But of course, this strategy is not optimized because we are not exploiting the flow. So we developed instead of the other two strategies, the surfing control and the perturbative optimal control, that in some sense are optimized, but are not really optimal because they are derived from assumptions of the real model, of the real system dynamics. So in particular, I don't enter into the details because I don't have time, but these two strategies have a common assumption behind. So they are similar because they have a common assumptions. That is that they consider that the gradients of the underlying flow that the active particle can measure at a certain time can be considered constant for an interval of time, tau s or tau p, that are the two free parameters for these strategies. Then anyway, these strategies are different because they are derived from different approximations, and in particular, the surfing control is thought to work better at large scale, so when the particles are far away, while the perturbative optimal control is thought to work better for small scale separation, and it is obtained as the zero-order solution of the optimal control problem. Now, let me just stress one point, that is that if we don't rely on the measurement that we perform about the local gradients, and so if we set the free parameters to be zero, then we recover the pure pursuit. Okay, now we would like to compare the performances of the heuristic strategies and the optimal control solutions. And so here I show the capture time statistics. So here I show the PDF of the capture time both in linear log scales. And as you can see, of course, here from this plot, we see that optimal control decreases the capture time better than the heuristic, but we already know that because optimal control is optimized by definition. On the right-hand side, anyway, more interestingly, I show the PDF of the normalized capture time. So here we have a comparison trajectory by trajectory. And as you can see, we have the PDF of the capture time of each of the heuristic strategy divided by the capture time of the optimal control. And as you can see, we have a sort of exponential distribution. So we have a high probability to perform close to the optimal control performances. So we have a high probability to be close to 1, but there is a non-zero probability to perform up to 5, 6, or even 7 times worse than optimal control. So here the message is that we show with this result that multi-scale and multi-time correlations are crucial to ensure optimality. That is something that is not, of course, taken into account by the reactive protocols. Okay, here instead we wonder about robustness of the optimal control solutions. So I said before that optimal control is obtained as a solution of a two-boundary value problem after the forward-backward search. So we wonder about robustness in terms of perturbations of the initial conditions. So what we did in practice is the following. We consider the control that would be optimal, so all the history in time of the control that would be optimal for a given initial condition, and then we apply the same control for a perturbed initial position for the agents. What we found anyway is that the perturbed trajectories are still able to become closer and closer to the target particles, so are still able to control the dynamics. And so in terms of dynamical system theory, we can say that the target trajectory becomes an attractor for the control dynamics. And this is more quantified here, where I show the PDF of the distance reached by the perturbed strategies. And as you can see, optimal control always decreases the initial distance, sometimes is still able to capture, while the heuristic strategies are not only worse, but they are even worse if we remind that they are reactive. So they are not really perturbed because they can continuously realign with the instantaneous correct control. On the right-hand side, instead, I show the finite time Lyapunov exponent. So this quantity quantify indeed the finite time fluctuations of the expansion rate for the particles. And so what we see here that optimal control always find more stable trajectories. Indeed, we always have negative values. And maybe more intuitively, we also see that larger capture times are indeed connected to more chaotic trajectories. Okay, so until now I discussed the case of equation-based methods, so optimal control or heuristic strategies that in any case have a model for the dynamics, but I don't have time to fully discuss the reinforcement learning case, so I don't have time to enter in the details of the method, but I just want to mention that we also published on our work for a similar problem of catching problem of a target that we publish on the PGE and in which we apply reinforcement learning techniques with the title Temi Lagrangian Chaos with Multi-Objective Reinforcement Learning. So now I want just to give you the key ideas of what is the typical setup that we can consider while working with model-free tool. So now we are in a partially observable environment. So now we should imagine that our active particles does not have global access on the entire velocity field, on the global velocity field, but they can only measure few properties. And the setup that we consider is the following. So now we have that both the particles can control the dynamics. So indeed, here there is the system for our setup. Alpha is the agency index, that can be 1 or 2. And capital U, the control variable now, has a velocity amplitude that depends on time. This is because sometimes the particles can decide to switch off the control and so simply be transported by the flow when it is favorable. This is because we are working with a multi-objective problem. So in this case, we want from one side to minimize the separation between the particles, but at the same time, we want also to save energy for controlling the dynamics. Also, to model the problem in a more realistic way, we imagine that the particles cannot continuously interact with the environment, cannot continuously sense the environment or receive signal from the environment, but they can only interact with the environment at some discrete times that we call decision time. Also, the particle can only have a very limited maneuverability, so they cannot steer in any direction, but in only few discrete directions. And they can only sense a very few information about the underlying field, as you can see by this coarse-grained grid. So they can only sense few information about the local gradients. And so this is completely different with respect to the previous setup. Now, I don't have time to show the results, but I just want to give you the key idea of what we can obtain. So I want to discuss the details of the policy, of the strategy that can be learned by reinforcement learning, but I want just to show this figure. That is that, as I said, we have a multi-objective problem. So it means that we have two competing goals, because from one side, we want to minimize the separation. So we want to be as close as possible to the target particle. But at the same time, we want also to minimize the cost for controlling the dynamics. So in principle, the best option here will be to be always passive. So what we can do with the reinforcement learning is to consider different trade-offs between these two competing objectives. And so we can learn different strategies that lies at the end on this frontier, that is the so-called Pareto frontier. So the strategies learned by reinforcement learning, or at least the performances, are shown with blue circles. And then in black, instead, you see what we call, again, heuristic strategies. So again, we are able to build some heuristic strategies for this new coarse-grained environment, a partially observable environment. I don't enter into the details, but of course, one possible heuristic strategy is the one that in which the agents always choose to navigate towards each other. Okay, I don't have time to explain more details, so I go to the conclusion. So we have seen that optimal control is optimized, and this is by definition. Anyway, it is model-based and is perfect information from the environment, and this is typical, something that is not possible to have realistic applications. However, surprisingly, it was very robust with respect to small perturbances on the agent starting conditions. So it is surprisingly because in principle, the uncontrolled system is chaotic. And then I didn't have time to discuss, but we also investigate that it is very difficult to apply the optimal control for large-scale separations. So for instance, in the natural range of turbulence. Then heuristic strategies need only partial information. They can be generalized also for large-scale problems, but of course are worse with respect to optimal control. And so the open question is how to fill this gap between heuristic protocols and optimal solutions, maybe with reinforcement learning. So I didn't discuss the method, but we know that reinforcement learning, it is optimized, but not by definition. It is optimized by the experience, so through trial and error. So with this, I think that I can conclude. So I thank you for your attention. And if you're interested, I give here some references.
Okay, thank you, Chiara. So let's see if there is any question. Yeah, yes, there are clapping hands, but not raised hands. So maybe I have, meanwhile, I have my personal curiosity. It's not, I mean, you mentioned that with reinforced learning, you are, your particle is experiencing the ambient from time to time.
Yes.
So, but I can figure out that also measuring is something which requires energy. So did, in your study, did you control also how the frequency of the measurements affects the quality of the results, and also maybe the distribution of the measurement, I mean, of the time intervals between different measurements?
Yes, of course. I didn't discuss, but in the so-called decision time, so that is the time in which we can interact with the environment, so we can measure the environment and we can update our control. So we can fine-tuning our control with respect to our goal. So of course, the strategy we obtain are strongly dependent on this decision time, and the performances are strongly dependent on this decision time. So in principle, what you have is that if the decision time, at least for our setup, let me say, but if the decision time is set to be 0, so you have a continuously updating of the control and a continuous sensing of the environment, at the end you reach this solution for the performances learned by from reinforcement learning. So a priori, you can demonstrate that you have this linear behavior for the performances between these two competing objectives. If the decision time is too large, so in particular, if it is too large compared to the Lyapunov time, then there is no way to control the dynamics. So controlling the dynamics or be passive is completely equivalent. So it's maybe in this case it's better to save energy, because in any case you are not allowed to minimize the separation between the particles, because your update of the control is too sporadic in this case. While in the middle, what you see is that for different decision times, you will see that you have different curves here, different concavity for this frontier. So of course you have a behavior that goes down for increasing decision times.
Yeah, no, this I could expect, but what I say is that if you want to save energy, maybe it could be convenient, but I think this is not in your approach. Also to optimize the number of measurements. So you want also to do the less measurements that still having a good performance. Okay, thank you.
No, yes, this is we just fixed the time for the measurement, but we didn't investigate this other point. Yes.
Okay. So thank you for your answer. Any other question? I don't see any. So then we can thank Chiara again. Let me also remind you, okay, that next seminar will be on the 14th of November. So we reconvene here in November. Thank you very much and bye bye.
Grazie a tutti, grazie.
Everyone. Ciao a tutti.
Ciao, grazie, ciao.
Ciao, ciao.